Here is a list of numbers. Split them into two groups. Now make the two group totals as close as possible. The smallest gap you can reach, that single number is our entire goal. And the secret to finding it is hiding inside one row of a table. The problem: partition the array into two subsets, S1 and S2. Minimize the absolute difference between their sums. Take 1, 6, 11 and 5. The total is 23. The best split is 1, 5 and 6, giving 12 against 11 on its own. The difference is just 1. Here is the key insight. If the first subset sums to S1, the other must be total minus S1. So the difference is the absolute value of total minus 2 times S1. To make this small, we just need to find a reachable subset sum S1 that lands as close as possible to half the total. But which sums are even reachable? That is the real question. So instead of guessing, we compute every single subset sum that can be built from our numbers. This is the subset sum dynamic programming table. We build a grid. Rows are the numbers we are allowed to use. Columns are every possible target sum from 0 up to the total. A cell is true if that sum is reachable using the numbers up to that row. Sum 0 is always reachable by taking nothing. Then for every cell, we ask one question. Can we reach this sum without the current number, or by taking it and covering the rest? Take or not take. That is the whole recurrence. And here is the beautiful part. When the table is full, the last row holds every subset sum reachable using all the numbers. We do not need a single answer cell. We need to read the entire row. So we sweep from 0 up to half the total, and at each reachable sum, we measure the gap. The smallest gap we find is the answer. What does it cost? Filling the table takes order n times total. Then one scan across a single row takes order total. So the time is order n times total, and the space is order total. Notice we keep that final row on purpose. It is not waste. It is the answer we need. Two quick pitfalls. First, scanning past half the total is harmless, but redundant. Symmetry already covers the other half. Second, do not space optimize away the very row you need to read. Here, the final row is the answer. So here is the big takeaway. A filled dynamic programming table is a data structure. Sometimes the answer is not a single cell, but a scan across an entire row. Reachability problems often end exactly this way. Learn to read the whole last row, and a new class of problems opens up. Can we hit a sum? How close can we get? Next, we change one tiny idea. Take or not take becomes take plus not take, and that unlocks count subsets with sum k. Thank you for watching.